Let's talk about division of segments. Here's my segment. It's bounded by 2 points, A and B. And let's say I want to divide it with a point G. And there's a certain proportion. I don't know the lengths involved here, but let's say I do know that I want 5 to 3. So I want a proportion of 5 to 3 for G. And how do I do that? So here, AG is the same proportion to GB as 5 to 3. Or we can write it like this, AG over AB, AG over GB is 5 to 3, 5 over 3. Now, this is an interesting problem. It's a very profound problem, actually, because it has very, very many consequences, and this technique is actually so fruitful. There was a book written by a guy named Beskin, and it's a really good book. It's called Division of a Line or something like that. And I think I'm going to do a whole video on division of segments, how to find this point G given AB and these proportion. I talked about this before in the Leonardo da Vinci video. I will leave a link to that video in the description box. Let's make it a little bit more general. Let's put an M and an N here instead of the 5 to 3. And the answer to this is G is N A plus MB over M plus N. Haha, fooled you. You thought it was going to be the other way around with MA and NB, but it's not. You have to be very careful about this. This is reversed, you see. It's reversed from this order here. Here I have M, N. A is near M, but here I put an N. Why is that? Well, we will see in this video. I'm not going to prove this here. I'm going to prove this plus many other consequences in a future video, but I'm going to show you why it's reversed. Now, in case you want to compute these components carefully, let's say A is a X, a Y, and B is BX, BY. Well, we want to compute G is GX, GY. We know the A's and B's, we don't know the G, from which we can calculate G by putting in these vectors or points and then just doing the calculation. We have N MBX over M plus N, comma N AY plus MBY over M plus N. And this is just GX, GY. These are the components of my point G. So you can think of these things as vectors or points with 2 coordinates. Now, I want to do something a little bit different. I want to relabel these things because these things here, A, B, M, N, and so on, because relabeling will make the construction that we will do in this video a lot clearer, especially in what we're going to do in this video. Let me relabel my segment diagram. Here I have V1 and V2. I'm anticipating using V for vertices of a polygon, a convex polygon. Okay, so let's say I put my G here. I want to divide it in certain proportions. Let's say this is 2 and this is 5. Okay, I'm going to call this P1 here and this P2. I've already reversed it. So the V1 is sort of matched with the P1 over here. I've already reversed them so that things will come out in order when I compute G. So if I do the same thing, my division of segment, I follow the recipe, I reverse these two, and I put P1, V1. Now V1 is associated with P1 and P2, V2. It's kind of like the gas law over P1 plus P2, like this. Okay, so now they end up in the sort of a proper order here in this formula, but here they are kind of reversed. But this is the way I want to do it. This makes everything a lot easier to follow. Now this thing has a name. We can call it weighted mean or weighted average. It's like the average. It's always inside the segment. That's something we can prove. Well, it's going to be a consequence of what we're going to prove today anyway. So this is like a generalized centroid or center of mass. And if I put my weights, P1 and P2 are my weights. And if I put my weights equal to 1, what happens if P1 is 1 and P2 is 1? Well, now my proportion is balanced. It's 1 to 1, you see? I have a 1 to 1 proportion and G is right in the middle. So I end up with G. G is 1 times V1, V1 plus V2, P2 is 1 over 2. And this is the centroid or the mean. You want to call it mean, average. Or, you know, if you think of this V1, V2 as a degenerate polygon that's only a one line, that's fine. This is also the centroid. So let's keep this in mind that centroid is it's a special case of weighted mean. So let's make a note of that. That's something very important to keep in mind. So if we can prove something for weighted mean, then we automatically can prove it for centroid as a consequence. That's very important. Now, the next question I want to address before getting on to polygons is why the reversal? For instance, if P1 is here and P2 is here, and I try to construct my G like this, well, this is absolutely wrong. Okay, so here I've taken the close one, P1 with V1 and P2 with V2. This is wrong. The correct one, as we talked about above, this is the correct form for segment division. The V1 is matched with the opposite side length, or not length, but proportion P1. Why is this so? Well, we can turn to physics to get an idea why. So once you see this analogy, it will all be clear. So let's say I have this bar and I have a very heavy mass here at point V1. P1 is the weight and P1 is heavy, and P2 here I have V2 at position V2 I have a lighter weight P2. Now of course this is wrong. You can't have something like this. You have to put the fulcrum here, and this is point G, and this is going to be P2. This is a small length here, small, and this length is P1. This is long, so this is big. P1 is big, heavy, and P2 is light, it's small, so P2 ends up to be proportional to this length here, and this length here, P1, is proportional to the weight here. Now, the actual numbers don't matter. What matters is the proportion, so this works. So we see, again, that the vertex V1 is matched with P1 on the other side of the fulcrum G. So that's why it works. Great, and so now that you see this analogy here, you will never make a mistake again. We need to have this really straight in our minds, because as we're walking around the polygon, we're going to apply this segment division many times, sort of left and right, upside down, and so we really have to practice this fact that the vertex weights are matched with the length proportion that's opposite on the other side of the fulcrum G. Now let me introduce you to the concept of a convex polygon. This is an example of a convex polygon. Why is it convex? Well, I can take any points on the polygon boundary or any points inside the polygon, draw a chord or a segment. So for example, like this, or maybe this way. It could be any points, even points inside the polygon. But that's kind of obvious. But okay, so any points, and I draw a segment. So you notice here that what's interesting is no matter what I choose as 2 points of a segment, the segment itself is always inside the polygon. Okay, so any segment, I could write it like this. Any segment between 2 points in the polygon is also in the polygon. And this works for a case like this here, for example, 2 points along the boundary. Those points are in the polygon. They're on the boundary of the polygon. So we say, okay, they're in the polygon. They're not in the interior of the polygon, but they're in the polygon. And this segment is in the polygon. It's along the boundary. These points of this segment here, these points, they're all completely in the interior. Here, we have 2 points on the boundary, and the rest of the points of this segment are in the interior. So this is actually a convex object. It has this property that the points of the segment, that you draw any segment anywhere, and the points of the segment are completely contained inside the polygon. Now let's look at something which is not convex. This here is not convex, and I can try it. Look, let's say I choose this point here and this point here. Okay, that's pretty good. All of these points on the segment are inside this polygon. However, if I choose this and this, no, these points are now outside the polygon, you see. And let's say I choose something like this, here to here. Well, I draw my segment. Some of the points, like, okay, I'll draw some, color some. These points are in the polygon, but these points here, out here, they are outside the polygon. So here they are in, and here they are out. So this doesn't work. This is not a convex object. So not convex. Okay, some segment points, or most of them, or some segment point, like in this case, almost all of them except the endpoints are outside. Some segment points are not in the polygon. They cross over to the outside, and so they're not a convex object. Now, objects like this, convex objects, are extremely important in mathematics. They have some profound mathematical properties. There's an entire science of convex objects, which maybe one day I'll get into. It's very interesting. It's not trivial at all, and the results are fascinating. It's really, it opens the whole vistas in mathematics, really. And you will see, like, once we finish this proof about convex object, in this video, we will use this proof to prove some profound results in the next video. You'll see. So this is not just an abstraction. This is a very important concept. I cannot stress how important convexity is concept in mathematics. So it's better to learn whatever you can about it right now. It's really important. Now let me state the main results that we are going to prove. First, let's say we have a polygon and it's convex with vertices v1, v2 up to vk. So these are my vertices. And let's say I weight my vertices. So I have weights p1, p2, and so on, pk. And these are my weights. So I have two important consequences. The first one is that the centroid of a convex polygon is always inside. Well, it could be on the boundary if it's a degenerate polygon, but it's always in the polygon. Okay, and remember, centroid is when all my weights are 1. So it's v1 plus v2 plus all the way up to vk. I have k vertices over k. I add the number of vertices up and I get k. So that's my centroid. This point is always inside the polygon. This is a profound truth, and it has many amazing spin-offs that we will examine soon. And another one is that a generalized version of this is that the weighted mean is also always in the polygon. And the weighted mean, if you recall, the weighted mean was this expression p1 v1 plus p2 v2 and so on. Okay, so for a non-convex polygon, these points may or may not be inside. It could be inside or could be outside, but for a convex polygon, they're always inside. What we're going to do is we will prove this one. We will prove this one because it's easy. It's actually pretty easy to prove this, and as a consequence, we just put p equals 1. You know, all our p's equal 1, and we'll be able to instantly derive the centroid one. This is the one we want. You know, well, we want both of them, but this is the one kind of I'm interested in proving, but it's easier to do it. Well, it's easy to do it both ways, but why not just start with the more general one and then just substitute p as 1, and then we get the centroid one. So what weighted mean really is then is like a generalized centroid where your vertices don't have the same mass. They have different weights. Okay, so it's the same thing as a centroid, but you've made it a little broader by allowing the weights to be different from 1. Okay, so it's the same concept. It's better to prove this thing. So we're going to prove that this point here is always inside the polygon. So we're going to prove the main result, that the weighted mean of a convex polygon is always inside, never outside. Our convex polygon will have k vertices. Well, actually, for my illustrations, I have to pick a number, so it's got to be 8. It's going to be 8. And each vertex is going to have a weight pi, p1, p2, p3, up to k. And let's start. All right. So let's begin with this. We'll create a sequence, G1, G2, and so on up to GK. We'll create a sequence of these sort of like sub-weighted means or partial weighted means. Let's call it partial weighted means. You'll see how it works. So we'll begin with G1 is V1. So we choose some vertex, and I chose this one. Could be anyone. We chose this one, and V1 has a weight of P1, and V2 has a weight of P2. So if I'm going to construct G2, which G2 is here, if I'm going to construct G2, you know, we discussed this in the first part of the vid. I have to put this weight P1 here and this weight P2 here. Now, my weights, I'll tell you what the weights are for this later. It doesn't really matter what they are, but you notice that P1 must be lighter than P2. You can see from where G is, because G is closer to P2, so P2 has to be heavier. So the first one, G1, is V1. And now G2, I can compute by our usual method. It's like this, P1, G1. Okay, so forget V1, we'll use G, you'll see why, and plus P2 V2 over P1 plus P2. Okay, so now I put back this G1 here. I substitute for that, and I have P1 V1 plus P2 V2 over P1 plus P2. So what is G2? G2 is weighted mean of V1 and V2. So it's like a partial weighted mean. It's not the weighted mean of all of our points of the polygon. It's a weighted mean of two of them. Also notice that I put here my final weighted mean, G. Okay, so we want to be able to get to this point. Right now we're here at G2. We started at G1. We're now at G2, but we want to get to this point here, G. That's our final destination. Next. So I have constructed G2 using weight P1 here and P2 here, and I'm going to continue this concept. Here I'm going to put the weight of the vertex 3, that's P3. I'll put it here, and here I will sum up P1 plus P2. That's the pattern I'm going to use. So over here I'll put a weight associated with the vertex, and here I will put the sum of all the previous vertices I worked with. The previous vertice weights were P1 and P2. Okay, so now I can compute G3. And by segment division, it's like this. You see the weight here is P1 plus P2, and the weight here is P3. And the sum of the weights is P1 plus P2, this here, plus this one. Okay, so I get G3. Now I substitute back. What was G2? Well, P1 plus P2. Let's put back what G2 was. G2 was P1 plus P1 V1. If you go back and look at what G2 was, it was P1 V1 plus P2 V2 over P1 plus P2 plus P3 plus P3 V3, like this, all over P1 plus P2 plus P3. We just need patience and try not to make any mistakes, and everything should go well. Things start to cancel out, and that looks interesting. Let's simplify this. Look at what we get. This is very interesting. Look at this. P1 V1 plus P2 V2 plus P3 V3 all over P1 plus P2 plus P3. So what is this? Well, G3 is the partial weighted mean. It's the weighted mean of points V1, V2, V3. Okay, so if we can keep this pattern going, then GK will be the weighted mean of all of them, and the weighted mean of all of them is the weighted mean. It's the one we're looking for, right? All right, let's continue this idea with another diagram. Right, okay, so here I have another diagram. Let's continue this idea. Over here I have the weight of vertex 4, which is P4, and here I will put the weights of all the other vertices that came before it. So P1 plus P2 plus P3. That's the pattern I'm working with. And this construction will give us what we want. So this is a particular construction that we have concocted, which will give us the final answer, G here. Okay, so we just have to prove that it works. We follow the pattern of this construction and we prove that it works. So again, keep in mind I'm matching this weight with this point here. And I have to match, let's use a different color, this weight here with this point here. So that's P4, V4. And then I have to add up all of the weights that I have on the right and the left of the fulcrum G4. That's P1 plus P2 plus P3. This plus P4. Okay, so I plug in now my G3. I plug this in. What I got that from the previous step. This is a bit like induction. P2 plus P3 over, and here I have P1, V1 plus P2, V2 plus P3, V3 over P1 plus P2 plus P3 plus P4, V4, all over P1 plus P2 plus P3 plus P4. Man, my hand is getting numb from writing this. Right, okay, so good things happen. This cancels with this, and I have P1, V1 plus P2, V2 over P1 plus P2, etc. And this, what is this? This is the weighted mean of the first four vertices, V1, V2, V3, V4. So you see the pattern, you see where this is going. Let's just complete the whole thing and do the last one. Well, we'll show you how the last one looks. Like so, I continue the construction. So I started here with P1 and here P2. This was P3 and this was P1 plus P2. This was P4. P1 plus P2 plus P3. Okay, P2. And you continue this. This is P5. This is going to be P1 plus P2 plus P3 plus P4. And you finish it. Okay, so that's your job. Finish it. This is a very interesting computation, and you continue. And if we continue this, G8 will be P1 V1 plus all the way up to P8 V8 over P1 plus all the way up to P8. And this is G. This is the weighted mean of all vertices. And you notice that when I did this computation, the G8 is now exactly on top of G. The green dot has replaced the black dot, and we have done it. Our G8 is, in fact, the weighted mean. For K vertices, this result looks like this. My kth G, okay, is actually my final answer, and this is the weighted mean. Now, let's reason about this a little bit more closely. Okay, let's think about this. Maybe I should make this bigger. All right, let's think about this. Now, the polygon is convex, yes? So every point along this segment is inside the polygon. So therefore, okay, so the segment V1, or actually we can say G1, V2 is in the polygon. So therefore, G2 is in the polygon. It's inside. Now, again, the same thing here. This segment, G2, V3, G2, let's call this polygon pi. So G2, V3 is completely in pi. Well, yes, pi contains the boundary. So, okay, we can say it's a subset of pi. And therefore, G3, the point G3 is inside pi. Okay, and we continue here. All of these points, because this is a convex polygon, all of these points must be in pi. So G3, V4 is inside pi. So therefore, G4 is inside pi. And we continue this until we know G8 is inside pi. Or, in fact, if I had put more vertices, or we'll just say GK is inside pi. So, okay. So, but we also know, okay, so this is the critical point, but we proved that GK is actually the weighted mean G. So therefore G, the weighted mean is inside pi. And we're done. We have proved that for any convex polygon, the weighted mean is inside pi. Very, very beautiful proof. Beautiful. Like that. For the previous computations, I chose the following weights. Like so, 1, 2, 3, so on. So if you want to duplicate everything I did and draw it your way, use those weights and you'll get the same result. But now let's try it with the same weights, all 1, like that. Or actually it would work if you just chose any number and made all the weights the same. You would still get the centroid. So now instead of weighted mean, G becomes the centroid. All right, and by the theorem that we proved above, G is in the polygon pi. So we did it. We proved that the centroid is in polygon pi. Simple consequence of what we proved for weighted mean. So let me show you what that looks like. This is what the computation looks like, and let me go through this with you. Maybe let me make this a bit bigger. All right, so let's go through this. If I choose, I'll begin by choosing a weight of 1 and 1. All the weights are 1, so that's going to be 1, 1. And this is going to be a weight 1, and this is 1 plus 1, so that's 2. And this is weight 1 and 3, 1 and 4, 1 and 5, 1 and 6, and then 1 and 7, and we get the final one, and we see it works. G8 is exactly on top of G, which is the centroid of this figure. It's very beautiful. Okay, so we're done. We are done. But I'm not going to say goodbye just yet. I want to give you something to think about. And the thing to think about is this. What if we choose a different vertex order? Like here I chose this to be G1 and then I constructed G2. I chose this to construct G2. But what if I had chosen this to construct, or some completely different order? I'll show you what I mean. This can be done with the centroid, no problem. This is what I get. I've chosen a completely different order. You can see here. Let's take some color. I started here, G1, and then this is the next one which I used to construct G2. This is a bit of a mess, but G2 is here, and this is 1 and 1, so I constructed G2 this way. And if you follow this around, you'll see what I did, and it worked. It works fine, so order doesn't matter. That's obvious because it doesn't matter in the centroid formula. I can just permute all of the v's and I still get the same expression. But this isn't exactly true for the weighted mean. If I permute the vertices, then I can actually get a different number, because the computation is going to work out differently, because it's not just vertices, it's vertices and weights. So my question to you is this. I can do it in any order for centroid. Order doesn't matter when finding the centroid. Does it matter for finding the weighted mean? If I do the computation in a different order, does it matter? Now, I'll just tell you that you can make it work. You just have to be a little bit careful, and you tell me, how can you make it work so that order does not matter? Okay, so you just have to be careful. If you approach it naively, it won't work, but if you're careful about it, it will work. So you tell me, how does that work? Well, we've reached the end. This was a lot of work, a lot of figures I had to draw. I hope you liked it. If you liked it, then click like. If you really liked it, then subscribe. Or do both, and I will see you next time. And in the next video, I will show you some amazing applications of this property of convex polygons. You think that this is all just abstract stuff, right? Oh, no. This leads to totally amazing results. You will see. It's pretty mind-blowing results, and that's coming in the next video. So I will see you next time.